Good morning, my dear student. On the behalf of KTM College, Nasik and Department of Chemistry of this college, I am Dr. S.R. Labhade welcomes you to the lecture on Hydrodynamic Voltammetry. Student, in previous lecture we discussed construction and working of working electrode used in Hydrodynamic Voltammetry. We discussed the construction of rotating disc electrode and rotating platinum electrode. We also discussed the advantages of rotating disc electrode over the rotating platinum wire electrode. Student, in today's lecture we discuss the instrumentation and working of hydrodynamic voltammetry. Instrumentation of hydrodynamic voltammetry. Student, we know that hydrodynamic voltammetry is a derivative technique of polarography. It is a derivative technique or derivative method of polarography. Hydrodynamic voltammetry is a derivative method of polarography, and therefore instrumentation of polarography and hydrodynamic voltammetry are exactly same. Therefore, in hydrodynamic voltammetry, a polarographic electrolysis cell, consists of a rotating disc or rotating wire electrode and a counter electrode is another platinum wire which may be stationary. Therefore, this polarographic cell consisting of here a inlet and outlet for removal of dissolved oxygen, there is a rotating disc electrode as a working electrode. This is working electrode. Again, there is provision to place a reference electrode. Here, reference electrode is a saturated carbonyl electrode. This is a salt bridge, and again there is third electrode which is again in wire form, that is a counter electrode. This polarographic cell having three electrodes. This is a stirring bar and this cell is placed over the magnetic stirrer. This is stirring bar, analyte solution. Here this is the provision for removal of dissolved oxygen by passing nitrogen gas. This is a working electrode. This is a saturated carbonyl reference electrode and this is a counter electrode. Therefore, here a polarographic cell, this hydrodynamic cell or electrolysis cell in hydrodynamic voltammetry is consisting of rotating disc electrode as a working electrode. Another counter electrode is a platinum wire, and this is a reference electrode. Reference electrode is used to control the potential of this working electrode, and counter electrode is used to complete the circuit between the working electrode for electrolysis process. Therefore, here working electrode and counter electrode carries electrolysis current, while saturated caramel electrode does not carry electrolysis current. It is a reference electrode. Therefore, similar to polarography, in hydrodynamic voltammetry, a rotating disc or wire electrode is used as a working electrode, while another platinum wire electrode is used as a counter electrode. Again, here similar to polarography, there is provision for removal of dissolved oxygen. Therefore, secondly, provision for removal of dissolved oxygen. Similar to polarographic analysis, in hydrodynamic voltammetry, the dissolved oxygen in analyte solution is reducible at working electrode. Therefore, it is essential to remove the dissolved oxygen from the analyte solution. Otherwise, the reduction current of dissolved oxygen is get added into the reduction current of the analyte, and therefore here there is also provision for bubbling the nitrogen gas in analyte solution in order to remove the dissolved oxygen from the analyte solution. Third component, that is again similar to a electronic circuit or a potentiostat for application of linear potential. Therefore, here similar to polarography, hydrodynamic voltammetry is a linear scan voltammetric method. In this case, potential of working electrode, rotating working electrode, that is scanned either to positive direction or to negative direction linearly. Therefore, here in order to increase the potential of this working electrode linearly, resistance of a cell decreases linearly. And therefore, here we can directly increase the potential of working electrode linearly. The potential is generally scanned at the rate 1 to 5 millivolt per second. 1 to 5 millivolt per second, that is a scan rate for linear increase or decrease in potential of working electrode. Generally, the potential of working electrode is scanned to positive direction linearly to carry out the oxidation of the analyte species. And if scanning potential is in the negative direction, then reduction of analyte species takes place. Therefore, in both cases, that is oxidation, a anodic current is measured, a reduction, a cathodic current is measured, and that current is then feeds to the recorder. Therefore, here the recorder is a current voltage recorder. Similarly to polarography, in hydrodynamic voltammetry, there is a pen recorder. Pen recorder gives a graph of cathodic current or anodic current as a function of applied voltage, and this current thus measured for determination of analyte concentration. Therefore, here a chart recorder or a pen recorder is used for recording the results obtained in voltammetric analysis. Therefore, instrumentation of hydrodynamic voltammetry and polarography are exactly same. Both techniques are linear scan voltammetry technique. Only difference is that polarography is performed in a quiescent analyte solution, while a hydrodynamic voltammetry performed in a solution which is continuously in motion. Another difference is that in hydrodynamic voltammetry, a stationary or a solid electrode is used, while in polarography, a dropping mercury electrode is used. Therefore, instrumentation of hydrodynamic voltammetry and polarography are exactly same. Student, now we discuss the working of hydrodynamic voltammetry. Working of hydrodynamic voltammetry. As the instrumentation of polarography is exactly similar to instrumentation of hydrodynamic voltammetry, therefore working of hydrodynamic voltammetry is again exactly similar to the working of polarography. Therefore, in hydrodynamic voltammetry, analyte solution is taken into a electrolysis cell containing rotating disc working electrode and a steady platinum wire counter electrode as shown in figure. Therefore, in hydrodynamic voltammetry, analyte solution is taken in an electrolysis cell where working electrode is rotating disc electrode or sometimes rotating platinum wire electrode, and counter electrode is another platinum wire electrode. Here, analyte solution, supporting electrolyte is added. Then, supporting electrolyte is added, and the dissolved oxygen is removed by bubbling the nitrogen gas. Therefore, similar to polarographic analysis, in this case we have to add the supporting electrolyte, that is excess of alkali salt which is not reducible at a potential where analyte is reducible. Therefore, any indifferent electrolyte is added in a reaction mixture here that acts as a supporting electrolyte. In that case, supporting electrolyte is essential in order to nullify the migration current. But here, stirring is carried out, migration current disappears. But addition of supporting electrolyte keeps this polarographic or hydrodynamic voltammetric cell to a lower resistance, and it is possible to determine the analyte at lower resistance. Otherwise, if supporting electrolyte is not added, then when analyte is completely reduced, then resistance of cell increases, and therefore it is difficult to analyze that analyte completely, and so supporting electrolyte is also essential in hydrodynamic voltammetry. The purpose of supporting electrolyte in polarography is to nullify the migration current. The purpose of supporting electrolyte in hydrodynamic voltammetry is to decrease the resistance of hydrodynamic electrolysis cell. Then this solution is electrolyzed. The solution is electrolyzed by increasing the potential 1 to 5 millivolt per second linearly, either to positive direction, in order to carry out oxidation of analyte, or to negative direction in order to carry out reduction of the analyte. Therefore, analyte is oxidized or reduced. Oxidation will takes place when we scan that potential to positive direction, that is less positive to more positive, or less negative to more negative. Therefore, when we scan the potential from less positive to more positive, oxidation of analyte species takes place. At that time we measure the oxidation current, that is called as anodic current. When we scan potential less negative to more negative, at that time reduction of analyte takes place and we measure the reduction current, and therefore here that will be the cathodic current. In case of polarography, we only measure the reduction current, because oxidation is not possible to a potential greater than 0.4 volt versus saturated carbonic electrode. But this limitation is not in hydrodynamic voltammetry. Therefore, in hydrodynamic voltammetry, we may oxidize the analyte or we may reduce the analyte. Reduction current or oxidation current is recorded on a polarigram, and a polarigram is obtained like this. Therefore, here a polarigram, that is a result obtained in polarographic analysis, and here it is called as hydrogram or a hydrodynamic curve. Therefore, hydrodynamic curve or Voltammogram. Voltammogram is consisting of a current as a function of current measured in microampere as a function of EMF in millivolt. And here, similar to polarographic analysis, here we have a step-set curve showing a maximum limiting current, and here this is a residual current. When we subtract the residual current from this maximum limiting current, then we have a limiting current, that is called as I limiting. This I limiting is directly proportional to concentration of analyte. Therefore, here in hydrodynamic voltammetry, we have a current voltage curve in which there is no oscillation in a curve. That means we have a curve in this fashion. There is no zigzag motion or oscillations in this current voltage curve. Therefore, we can exactly determine the limiting current from this curve by subtracting residual current from the maximum limiting current. This limiting current thus obtained in this hydrodynamic voltammetry is directly proportional to concentration of analyte, and it is related with different factors. Therefore, I limiting is equal to 1.55 into n into f into a into d raised to 2 by 3 into mu raised to minus 1 by 6 into a pi raised to half into n raised to half into c. Now here the limiting current is given by this equation, and which is equal to the concentration of analyte. Therefore, here concentration of analyte is determined by this equation. In this equation, here I limiting means a potential dependent limiting current in microampere. Here N is number of electrons involved in redox reaction, that may be reduction or oxidation, therefore redox reaction. F is Faraday constant. Here D is diffusion coefficient in polarography. In this case it is called as convection coefficient. Convection or a diffusion coefficient of the analyte. Here mu is a kinetic viscosity of the analyte solution. Kinetic viscosity of analyte solution. Kinetic viscosity mu is equal to, it is given by kinetic viscosity of analyte solution mu is equal to viscosity of solution divided by density of the solution or solvent. Therefore, kinetic viscosity is a ratio of viscosity of solution to density of solution, and it is equal to mu. Here pi, that is constant, and N is equal to rotation rate of the electrode. That is revolutions per second, that is a rotation rate. And here C is concentration of analyte in millimole. Therefore, similar to polarography, here in hydrodynamic voltammetry, concentration of analyte is measured in millimole. Now here, limiting current is directly proportional to concentration of analyte, and it is given by this equation. Therefore, here limiting current directly utilized for quantitation of the analyte that undergo either reduction or oxidation at working electrode. This limiting current may be either limiting current because of oxidation or limiting current because of the reduction. Therefore, at 1/2 of the limiting current, whatever the potential, that is again a half wave potential. And this half wave potential is the identity of the substance. Therefore, here identity, or we can carry out the qualitative analysis of the substance by measuring the half wave potential. Half wave potential is the reduction potential of that analyte, and it is determined by this way, that is at 1/2 of the limiting current. What is the potential? That is a half wave potential. Half wave potential is the identity of the material. We can carry out the qualitative analysis, and limiting current is directly proportional to concentration of analyte. We can determine the concentration of analyte from the limiting current using this equation. Therefore, both qualitative as well as quantitative analysis is performed in a hydrodynamic voltammetry. Student, this is all about the instrumentation and working of hydrodynamic voltammetry. In next lecture, we discuss the applications of hydrodynamic voltammetry. We stop here. Thanks for joining with me. Wish you all the best. Keep learning. Happy learning.